Welcome to this class, Aspects about Product and Production, Part 4. This is the final part of our suite of classes dedicated to these aspects about product and production defined. The outline. We will start with the study of the plant capacity and its contribution. Then we will proceed to the concept of economies of scale. And finally, we will explore the link between the plant capacity and the production program. When it comes to the first two elements, it's very important to recall that the difference between the feasible nominal capacity and the nominal maximum capacity that we have explored during our last class, it's based on the fact that not everything that is installed could be feasibly exploited by the company. So crucially, the study of the plant capacity, the degree of contribution to the economics of the project, and the concept of economies of scales are central in order to appreciate this difference. Let's start with our first element, the study of the plant capacity and its contribution. Plant capacity and contribution. Let's refer to this picture here in order to observe what the contribution might be. So on the horizontal axis here we have the quantity Q1, Q2, Q3. On the vertical y-axis here we have the fixed costs, different levels of fixed costs. FC1, FC2, FC3. Now we have three scenarios related to sales. P, pessimistic, E, expected, R, optimistic. As we will see in our further contents, it's always better to figure two or better three scenarios in order to have different estimations of different levels of cost and exploitations of the installed plant capacity. Now, we have three scenarios, P, E, O, pessimistic, expected, and optimistic, and the different quantities Q1, Q2, and Q3 refers to these three scenarios respectively. Now, considering the hypothesis that the price is fixed, the level of sales and incomes could be related to the quantity in a proportional way. So if we consider the price as a fixed element, the unitary price is going to be the coefficient for estimating the revenues associated to sales. So the yellow line, which is proportional, linearly proportional to the quantity, express the level of sales per different quantities. The blue line instead depicts the fixed costs of the investment. So for Q1 we might refer to this level of fixed cost. If we install a bigger plant, we might have an additional capacity which is more expensive for the company. So this level of fixed cost number 2 is higher than fixed cost number 1. And fixed cost number 3 here, it's even higher. So we have this kind of ladder here scaling up the fixed costs. Now, if we have this first scenario, Q1, then the level of sale is just sufficient for covering the fixed cost. So if we have a higher production and sale, a higher level of production and sales. So between Q1 and Q2 here, we have the level of sales which is lower than the fixed cost. So the difference, this triangle here between the yellow arrow sales and the blue line, which is angled here for the action on the different levels of the fixed cost, is negative. So in such a scenario, sales are not sufficient for covering the fixed cost. In scenario Q2 and Q3, situation is different, since the level of sales is way higher than the fixed cost. So in the optimistic scenario, the contribution is positive and this area is bigger than the expected scenario. So this is to say that sales might contribute to the coverage of the fixed cost, and the definition of these levels of fixed cost is crucial in order to estimate the profitability of the investment itself. So plant capacity, which is a decision related to the installation of the facility capacity and accordingly to the level of fixed cost, is crucial for defining the contribution of sales to the coverage of the fixed cost. This is a static analysis related to the fact that sales might be able to cover fixed costs. In order to appreciate a little bit better the difference between the feasible and the nominal installed capacity, it's important to introduce the concept of economies of scale. Economies of scale. As the size of installation increases, the unit cost of production normally decreases. Now, what is important to depict is the action of size of the installations on the unit costs. So, as we will see momentarily, as the size of the plant increases, normally the unit costs decrease. Within the so-called minimal installed capacity, there is an economic convenience in buying and installing bigger machinery and equipment in the hypothesis of full exploitation of such capacity. So, graphically, we might observe that economies of scale could be appreciated by the confrontation of unit production costs versus feasible normal capacity. Now, let's consider on the horizontal axis the quantity, which is the plant capacity, in terms of feasible normal capacity. And on the vertical axis here, on the y-axis, we have C, which is the unit production cost. Now, the unit production cost could be represented in a curve of such a shape. And the formula explaining this shape of the curve is C, unit production cost, equals to A, which is a constant manufacturing parameter, times Q, which is the quantity, again in terms of feasible normal capacity. And here we have this exponential, which is M minus 1. Now, M, as we will see, it's the so-called correlating exponent. And parameters A and M depend both on project characteristics. So, for example, A is quite an influence for the shape of the curve, but M, being the exponential, is very influential on the shape of the curve. So M assumes values between a number which is close to 0 to 1, and it is 1 for labor-intensive productions, as we will see, when there is same contribution between labor and technology. If we have more, or if the impact of the capital is higher, so we have capital-intensive production, then M is lower. So as we will see, by referring to other graphs, the idea is that considering the correlating exponent, which is the level of employment of technology and personnel, considering the impact of technology on the production aspects, this curve might assume different shapes. The general idea, apart from the specific formulation, is the fact that as the plant capacity increases, the level of the unit production cost decreases. So this effect is the effect of the economies of scale. So as the scale expands, the average, the unit cost, unit production cost decreases. So the idea is that this effect occurs within the so-called minimum economic capacity. So, as we were saying, the coefficient A and the exponent M can be determined fairly from a minimum of 3 representative situations. So 3 scenarios: pessimistic, expected, optimistic. So considering 3 scenarios instead of 2 would give us higher confidence of results. So again, pessimistic, expected, optimistic. In order to estimate the impact of the economies of scale, as we were anticipating during past class, we should refer to different rules of the thumb, so to different heuristic solutions. So the first one is related to the impact of the power law and sizing model upon economy of scale. So the idea is that in the early stage, we have an incomplete data set, or we don't have all the possible information for defining the profitability of the project. So we could estimate the impact of the economies of scale by referring to 4 possible parameters. So we have C, the estimated parameter, Q, which is the size, the capacity of the system, that could be feasible or nominal, as we've seen. Then we have some reference value, both for C, the cost, and Q. So CR and QR. And then we have the correlating exponent, as we've seen. So C divided by CR could be equal to Q divided by QR, and M could be considered as the exponential. This is the first way for estimating the impact of the economies of scale. What is the limit? Power law applicability limits. The power law for determining specific investment cost per unit of outputs does not extend through the entire range of plant capacities. So it's a kind of punctual value that could be determined in certain ranges of values of the analysis. One way for depicting such a situation is to consider the idea of economy of scale considering capital cost ratio versus capacity ratio. So here we have the cost ratio, C divided psi R, which is the first part of the equation that we just seen. Then we have the capacity ratio on this X, which is Q divided QR. Now, when m, the exponential, is equal to 1, then we have a proportional distribution of the cost ratio according to the quantity. So, m is equal to 1 when we have labor-intensive production, as we've seen already. And so the yellow line depicts the proportional scenario. If m is lower than 1, 0.6 in our example, then the cost ratio has this kind of shape. The curve has this kind of shape. So it's higher than the proportional hypothesis in a certain range, and it's lower than the proportional scenario in another range. That's why the power law does not occur for any possible plant capacity. So if we are between 1 and 2 in this scenario, we might consider the effect of the economies of scale if m is lower than 1. This idea of having a specific range of applicability of economies of scale help us define the minimum economic capacity. So we should analyze the unit production cost, UPC, versus the plant size at a full capacity of utilization. Now, let's record the idea of full capacity utilization. The mere availability of a bigger plant does not imply that we can exploit economies of scale. We need a bigger plant and we need a full capacity utilization in order to lower down the unit production cost. Further, determine limiting production costs for local conditions. So local conditions, as we'll see, might influence the production cost as well. And then determine minimum economic size. So where unit production costs, UPC, are lower than the highest acceptable viable for industrial subsector. So it's not just a technical analysis in the sense of defining production capacity, but it's also a competitive analysis that considers what are the levels of unit production costs which are acceptable in such an industrial subsector. Minimum economic capacity. As this graph will show us, the minimum economic capacity comes out of the confrontation between the unit production cost, UPC, and the plant capacity. So in this graph we have two axes. The vertical one is the unit production cost, which is quite similar to all the ones we have seen already. On the other axis we have the plant capacity in terms of feasible normal capacity. So it's the actual exploitation of the plant. Now, this dotted line is the limiting cost, which is the consideration of the confrontation of the UPC, the unit production cost, with the rest of the subsectors that we're operating in. So we have this curve which is the shape of which is embedding the hypothesis of economies of scale, but if this is the limiting cost, this is the minimum economic capacity, which means that we need a plant with this minimum capacity in order to compete with our competitors in the competitive arena. Another important element is the relation between the plant capacity and technology. So the idea is that considering always the same axis, unit production cost on the vertical one and plant capacity in terms of feasible normal capacity on the X one, the horizontal one, we have three types of technology in this example. Technology type 1, technology type 2, technology type 3. Now, this is the shape of the single curves related to specific plans embedding different technologies. The dotted line here is instead the envelope of the UPC local curves. So it's the envelope of these technology-specific curves. And so according to the applicability ranges, number 1 for technology 1, number 2 for technology 2, and number 3 for technology 3, the company should choose technology which is guaranteeing the respect of the minimum installed capacity, as well as the cost conditions which are consistent with the strategic considerations that we've done so far. So, inventory build-up to minimize plant capacity. So, minimizing the necessary capital investment is in the best interest of a project. So, considering that investment requires some costs and implies some expenses, the definition of the minimum size capacity has financial and economic implications as well. So we should consider the demand fluctuation, seasonal, cyclical, and etc. And as we will see, fluctuations imply that the capacity should be consistent with the maximum peak of the production required, or we should schedule the activities in the way that when we have lower demand, we should keep on manufacturing our products in order to face times with higher demand. Second, when demand is lower than the planned capacity, inventories will be built up to a level to meet the expected higher demands in the future. So graphically, the situation is quite clear if we consider the inventory build-up to minimize plant capacity. Let's consider this graph. We have the sales program on one hand and the period, so time, on the other hand. And here we have the production level, which is associated to the minimum plant capacity or to the installed plant capacity. Now, the point is that during different periods of time, as you might see, we have production levels, feasible production levels, which are way behind the maximum production level. Sometimes, instead, we have a demand which is exceeding the production level. So the sales program for seasonal and cyclical production could be shaped in the way that, considering the installed capacity, sales could imply to sell products which are beyond the production level. Now, inventory build-up could help the company to storage this extra production which is needed in periods in which the maximum production cannot be sold in the market. So, considering the inventories could buffer the exigencies of the plant capacity. So, the maximum plant size, it's another idea which is related to the installation. So, we are familiar with the minimum plant size, but we might have a maximum plant size as well. So, type of technology could influence the maximum plant size as well, meaning that being the maximum plant size, the quantity after which the unit production costs keep on rising again, technology could be so flexible to render the production range sufficient for enabling the maintenance of steady minimum costs. To some extent, though, at a certain point, coordination mechanism or conflicting resources could, by technological reason, rise up the costs again. Another important element is the plant location and the transfer costs. So, to some extent, bigger facilities or larger installed capacities could require a more expensive infrastructure in terms of internal transportations or storage docks or other internal services of the plant. So, it's not said that the size could be increased ad infinitum, but at a certain point there are additional costs or additional elements that are constraining the maximum expansion of the plant in economic terms, meaning that the effect of the economies of scale could be limited or contrasted or tackled by the development of these economies of scale. Again, availability of materials and supplies could be another constraint to the another reason for the maximum size. In agriculture, for example, there is, or in the oceanography, there is the idea of sustainable yield, which means that the plant or the installed capacity could not be exploited in an efficient or effective way in an amount which is higher than prescribed. Then we have environmental constraints when it comes to pollution and when it comes to respect of external environment. As we will see during the last class of this module on technical analysis, sites could imply different standards in terms of sustainability as well. And then we have reliability and strategic factors, meaning that on one hand, the company and the project should face the fluctuation of demand. On the other hand, the economic sustainability of the investment should be considered in any minute alongside the investment deployment. The final part of our class is about the plant capacity and the production program. So, it's about the definition and the interaction between the decisions about plant capacity and the actual program, which is related to the deployment of productive activities. Production program and plant capacity. The plant capacity defines the quantity of production possible under existing operating conditions for the plant design. So, the plant design again is fixing the nominal maximum capacity, whereas the operating conditions and the plant capacity are based on the feasible normal capacity. Let's observe the link between the two entities, plant capacity and the production program, considering this scheme. Linkage of sales and production program. So, let's start from this side. We have demand projections, demand estimation, market penetration, and sales projections. And then, after the sales projections, we have the sales program. So, this part, it's something that we are very familiar so far, since it comes from the marketing side and has been recalled several times in the production-related issues. Then we have the definition of plant capacity that we have just seen, and after we have defined the plant capacity, we have to establish two other sub-elements, the production program and the production schedule. So one thing is to program the activities in terms of objectives and sub-goals we should achieve, and the definition of the required resources. On the other hand, we should schedule, so we are adding the time variable in order to deploy such activities. So to be a little bit more specific, The purpose of production program and schedule can be summarized in the definition of, so it's aimed to define planned production for each period over the life of the project. So it's a schedule in terms of time periods for each phase of the project. Further, it's about the decision on when to produce, mostly for cyclical production. So if we are producing ice creams in one country exposed to one weather, we have a peak of consumption during the summer, and then we have the lower part of consumption, eventually zero, during the winter if it's very cold. So for cyclical production, it's very important to not only to decide how and what in terms of volume and technology, but also when in terms of scheduling. Accordingly, if we schedule the production, then we have to schedule the procurement of materials and supplies. So it's not just about the plant capacity and the exploitation of the plant capacity in terminal terms, it's also about the interactions with our suppliers for materials and other supplies. And then we have the in-plant storage requirements. So what we've seen is that to build up internal inventories is one way to face fluctuations of demand. So in order to maintain our installed plant capacity in a range of sustainability, we cannot expand the plant capacity just following the fluctuations of demands and sizing the plant according to the maximum extent of the level of demand. So since we have to store both materials and final products according to the sales program, then the in-plant storage requirements are another relevant part of the production plan, the production program. So this is the mission of the production program and schedule. What is the output? To provide essential information for operating cost estimates and cash flows. So let's reflect a little bit on these elements. Essential information for operating costs are crucial for the estimation of the profitability of the investment itself. So we have to estimate the operating costs as well as to estimate the cash flows, cash in and cash out related to the management of production. So we have cash in if the production program is linked to the sales program and is generating revenues for the company. We have cash outs anytime that we have to face our suppliers, for example, both for technology and for materials and other supplies. Then we have the output in terms of production program determining what will be produced. So to recall an idea that we started from in the last class, is not only about products, which is the central part of the production program by definition, but it's also about byproducts, its storage and its usage as well. And it's also about wastes and effluents that should be disposed in a proper way. So again, production program, as we've seen, is not just about the core products, but it's also about the byproducts and the wastes coming out of the production process. Time is very important, so the production schedule determines when will be produced. And it's crucial for cyclical and seasonal productions, but it's required for all the productions, being the market unstable and being the company exposed to the fluctuations of markets by definitions. The last element is to consider the variations in production requirements due to cyclical or seasonal phenomena, as well as the intermittent production requirements in regards to capacity. Now, we should be familiar with this element so far, since we've seen already that cyclical and seasonal productions could be more exposed to the sensitivity of the program, to the time in which the activities are deployed, so in which the operational capacity of the plants is exploited. But for intermittent production, requirements are crucial as well. So when it comes to intermittent production, that one could be a choice of the company, and this is a very important link to what we will explore during next class, which is dedicated to the employment of human resources in the production activities. So intermittent production could mean, for example, that within the same year we have some months of production and some months of storage and sales, but it could also mean that if we have a plant that could work nominally for 24 hours a day in a row, so in a three-turn schedule, if we just exploit it for 8 hours or 16 hours, we have a kind of intermittent production. Meaning that from one turn and the next one, we might be exposed to some setup issues, as we've seen already with other elements. So, to sum up, it's important to define the plant capacity, not only in technical terms, but also in terms of economic sustainability of the plant capacity installation. Second, plant capacity is dependent on the effect of economies of scale, which is again the relation between the size and the shape of the unit production cost curve. And in order to exploit economies of scale, being considered the feasible normal capacity, we should face with the minimum and the maximum capacity of the plant that we could install and exploit. Once we have defined the plant capacity, then we have to link this consideration to the production program and the production schedule. So again, it's not only about technical definition, but it's about economic considerations as well. So production program implies activities, objectives, expected outputs, and timing for such activities. As usual, you can refer to our website for further information. That's everything for today. Thank you.